All right, so this is lecture 19-ish, I guess, for our distributed energy resources class. And today we're going to be talking about machine learning and specifically a type of machine learning called regression. And actually, I debated a little bit the order of this lecture and Thursday's lecture. Um, Regression and optimization under uncertainty. So regression basically is an application of optimization methods, not always convex optimization methods, but for the way that we'll approach it in this class, we will talk about it through kind of a convex optimization framework. But basically, regression is a way to either use data to fit a model of a system. So for example, to get the thermal resistance between your apartment and the outdoor air, you could look at thermostat data, energy usage data from your heating system, things like that. So we'll go through an example of that today. But also maybe you want to forecast something in the future. You want to make some decisions about how to charge and discharge a battery over the course of a day. It might be relevant to know how much solar power you can expect from your panels or what the price of electricity is likely to be. And so, usually we don't have perfect information in advance about those things, but we can use data to make predictions about them. So that's really what this lecture 19 today is about. And then Thursday's lecture is kind of like, well, if you're in that world where things aren't perfectly certain, you have some model of your building, but it's not a perfect model. Or you have some forecasts about solar power production or energy prices or something like this, but they're not perfect forecasts. So how do you basically incorporate some uncertainty in your decision-making process so that you are maybe more robust to unlucky realizations of solar power output or a high price period or something like that. So these two really kind of feed into each other, and it wasn't really clear to me in what order to present them. But we're just going to go ahead and talk about regression and predictions and things today, and then we'll talk on Thursday about basically how to use them in sort of decision-making framework. So any questions about logistics or anything like that before we get into lecture? All right. So the topic today is regression. Again, a type of machine learning, and we'll talk about a little bit of vocabulary and kind of taxonomy of machine learning problems before we dig into regression modeling and some solution techniques. So we'll begin kind of with an overview, again, of ML and regression in particular, and then we'll do two examples. And one is kind of a ginned-up mathematical example, basically says you have some function and you want to approximate that function, maybe with a polynomial, possibly a very high degree polynomial. How do you come up with the coefficients that should show up in your polynomial function in order to fit the data that you are given? So that basically is to showcase some features of sort of the process of regression that we'll talk about in part one. And then in part three here, we will do a little bit more concrete example with a DER application, which is fitting the thermal resistance to a building model from data from a thermostat. And we'll use some real data there. Okay. So machine learning in general is, I think, as everyone probably knows, a very hot academic and industry field. Encompasses an enormous range of applications and methods. But broadly speaking, the goal is to extract some information from some data. And often we do that using past data in order to be able to make predictions about what future data will look like. And so ML or machine learning in general kind of includes two tasks. One is to build a model based on your data. We'll talk about what a model is, but basically it's a function, a mathematical function that takes some input data and returns some output data. And ideally that predicts output data in the future reasonably well. And then the second task is to validate the model. So once you have built a candidate model, to be able to check how well it's likely to perform on sort of unseen data that might arrive in the future. So within the world of machine learning, there are at least two categories called supervised learning and unsupervised learning. And in supervised learning, which is what we'll talk about today, the basic idea is that you have some targets. So these are the outputs of your model that you want to predict. And then you have some inputs to your data, which we call features. So the model, again, is basically a function that takes in features and gives back targets or predictions of targets. And within that category of supervised learning, we can again sort of divide the problems into two problem classes. And one is regression. This is today's focus. And the idea here is that we have continuous or real valued targets. So they're just numbers, 1.876 or pi or something like that. And then by contrast, the other kind of sub bucket within this bucket of supervised learning is called classification. And so they're the targets, the things that we're trying to predict, rather than being kind of a continuous variable, they would be a discrete thing. So it could be yes or no, true or false, or it could be a number in some finite set, 1 through 10, Monday through Friday, something like that. And so the reason that we make this kind of subcategorization is that we typically use slightly different methods and different model structures and things like that, depending on whether we're doing regression or classification. And again, today, we're going to be talking about sort of real valued targets that we're trying to predict. And then another type of machine learning is called unsupervised learning. And the idea there is just to sort of build a model of the data. And the model should recognize patterns within a data, like for example, a data set. For example, there seems to be a cluster of data kind of in this region, and they share these particular characteristics, things like that. And then, the world of modern generative AI is kind of roughly in this machine learning world. And a generative model, I guess, is another class of model, but it's pretty much basically fitting a distribution of data and then generating samples from that distribution. So the responses that come out of ChatGPT are a little bit random. If you ask it the same question a few times, you'll get a few different answers. And so what it's doing is sort of sampling from an underlying probability distribution. Okay. All right, so again, just throwing some more vocabulary out at you guys related to machine learning. But as we build a model, and specifically a regression model, our real goal is to be able to have a model that we can, in the future, feed some unseen input data to, some unseen features to, and get back some predictions that will match some unseen targets in a reasonably good way. And by unseen, I just mean that this is data that we're not exposed to, we're not able to access while we're doing the sort of model building and training and validation process. So it's new data that will arrive at some future point. Okay, so unfortunately, while we're doing the training and building the model and validating the model, we don't have the unseen data yet by definition. So we can't really use that as our benchmark. And so, or use the model performance on that unseen data as our benchmark. So as kind of a stand-in, it's typical to divide your data into two kind of subsets, one that we would call the training data and one that we'd call the validation data. And so the training data we would use for choosing what type of model, what should its structure be? Should it be a neural network or a linear model? We'll talk a little bit about each of those. And also for fitting the parameters, the internal numbers that go into sort of that model structure. And those are sometimes called weights within the model. So this is the data that we use for those processes. And then we basically hold back some data. We treat some data as if it is unseen. So we basically hide it from ourselves, use a subset of the data to do the training and so on, and then check periodically on the validation data to see how well things are working. And the idea there, the intuition, is that if you can build a model that works pretty well in your validation data set, then the odds are pretty good that when you see some new data, some unseen data, that your model will work there well too. So this training and validation split is a way to combat the challenge of what's called overfitting. So when a model is overfit to data, really it means overfit to the training data. That means it performs well for the training data. So the data that you're using to fit, say, the numbers that go into your model fits very well on that set, but you use it for a different set of data that maybe have some slightly different characteristics, and it performs poorly over there. So that tells you that your model is overfit to the training data and likely will not generalize well to unseen data. And generalization just means basically if you make good predictions in training, you also make good predictions on that unseen data. Okay. So the flow of this section, again, we're going to go through a few sections here, mostly examples. The flow of this section basically is I'm going to, again, just keep throwing some vocabulary at you. It's going to have some equations and stuff built into it, and it's going to have some fairly sophisticated ideas. And then we're going to walk through what those ideas look like in each of these examples. So one process that we do when training machine learning models, building machine learning models, is called embeddings. So the idea here is that we have some raw data, call them U, and here the notation, the superscript with the parentheses I, is indicating basically the number of the training examples that were given. So maybe we are trying to come up with a model to predict the energy consumption of a community. And we would have a bunch of U input data, that variables that could have some predictive information about energy use. So this could be the outdoor temperature. It could be something related to sunshine. It could be something related to the day of the week, whether it's a holiday or a weekday or a weekend. It could have information about the hour of the day as well. And then in the load prediction case, the output here might be the energy consumption of the whole community. So this might be a number in kilowatts, for example. And then I here, so you'd have a bunch of days, hours, weather conditions, et cetera. You'd have a bunch of examples. And you'd have a big vector of all the possible kind of input data. And then you would have a number or a vector that represents the corresponding output data. So you'd have something from Tuesday at 1 p.m. and that would be I equals 1. You could have Tuesday at 2 p.m. and that would be I equals 2 and so on. Okay, so these are the raw data. And then the process of embedding is basically mapping that raw data into the actual features that will go in as the sort of inputs to our predictive model. So we come up with some function phi. This is called the feature embedding. That takes our raw data. So again, this could be a label like Tuesday or weekend or not weekend, something like that. And it maps it into something else, a vector valued feature here, x. So here nx would be the dimension of that feature vector. And it's not necessarily the same as the dimension of the u thing here. And this U stuff could be not necessarily numerical data. So again, it could be a string. It could be the day of the week or something like that. But generally, X here would be numerical. So it would be a number. And then we can do the same thing on the outputs as well. Potentially, we don't always do it, but we could. And so these transformations here, phi and psi, that basically map the raw data into the feature for phi and raw output data into the target, we call embeddings. And so for the rest of this lecture, we'll just assume that the thing that we're trying to predict, the target y, is a scalar. So just a number. But all the methods that we're going to talk about today work equally well with minor modifications when you're trying to predict a vector of things. So the distinction there might be trying to predict 1 hour from now, trying to predict the power consumption for a community, as opposed to trying to predict, say, a vector, a trajectory of power consumption over a day or a week, something like that. Okay. And then a desirable property of embeddings is what's called faithfulness. So a faithful embedding basically satisfies that your embedding, so this would be the feature, so the transformation of your input data, phi of u, that those things are only similar for two different U and utilities, so two different input data values, if the input data are themselves kind of similar, close together. And there are different ways to measure sort of what closeness means. But let me walk through this in one example. So suppose that we, again, maybe are trying to come up with an energy, sort of baseline energy prediction model for a community. And we know that time of day is an important feature. Community is going to consume a lot less energy at 4 in the morning than it would at 4 in the afternoon. So for each of our kind of examples that we have in our data set, which maybe is a month of data at hourly time resolution, something like that, we would basically have an hour of day value, 0 through 23, where 0 is midnight and 23 is 11 p.m. So this is the set of possible input data for this feature, the hour of day, the hour of day variable. And we want to come up with a faithful embedding so that basically, if the hour of days are similar, then our function phi of u, the embedding, is similar. Okay, so an issue right away, if we just, one idea would be just to say, use this directly as our feature. So just directly put into the model a number between 0 and 23, an integer between 0 and 23. That would not be a faithful embedding because midnight here, which would be 0, is a similar hour, right, to 11 p.m. They're only sort of 1 hour off, but they're basically as far as they can be from one another in this sort of raw data set, right? Because 11 p.m. is 23 and midnight is 0. So an idea to overcome that would be to choose an embedding here, which is sinusoidal. So maybe we take the sine of 2 pi times our feature, this thing between 0 and 23, and divide it by 24. So this thing would basically run between 0 and 2 pi would be kind of the inputs to this, and then the outputs would be -1 to 1. Okay, then this thing has kind of a periodic behavior, and we chose the period basically by the denominator, the 24 here. And now that this looks a little bit better because phi of 0 here, sine of 0 is 0. And phi of 23, well, that would be sine of 2 pi times 23 divided by 24, which would be very close to the sine of 2 pi, which is 0. So these are now close together. The hours are close together, and things look okay. But there's another problem. So this is really an if and only if sort of thing. And we've kind of satisfied one direction here, but the other direction still doesn't work. So to see the problem there, midnight is about as different as can be from noon. So, but 0 and 12, which would be the hour for noon, are actually, with this embedding here, the sinusoidal embedding, they actually give the same value. So if we plug in 0 up here, or if we plug in 12 up here, we get sine of 0 or sine of pi, which are both equal to 0. So now we have dissimilar sort of input data, but the feature is actually similar. So a way to resolve that would be to use an embedding that actually increases the sort of dimension. We go from having a scalar input in this set U, just one number, to having a vector, which would basically be the sine and the cosine with the appropriate adjustment for a 24-hour period. Okay, so in this way, let's see what that looks like. So each of these features would run between -1 and 1. So here I'm plotting -1 to 1 on the x-axis and on the y-axis. And then let's see, when we are at, say, u equal to 0, we would have sine of 0, which is 0. So it would be here. And then the cosine of 0 is equal to 1. So we're up here at the point 0, 1. So here's where kind of 0 would be. And then we were worried about 0 and noon being similar. So let's look at the hour 12. So again, we would be at 0 here. Sine of pi over 2 is equal, or sorry, sine of pi is equal to 0. But the cosine of pi is equal to -1. So now 12 and 0 here are dissimilar times, and they're also dissimilar features here. So more or less, we've kind of reinvented the clock here. I guess this is the 24-hour clock. But we're sort of good. So midnight and 11 p.m. and 1 a.m., these are all kind of close together. And those are all sort of similar hours of the day. Okay. All right, so that's the idea behind embedding. Rather than just sort of naively taking our raw data and throwing it into a model, we do some transformations on the raw data in order to get basically better predictive information out of that data. It makes sense. Okay, some other very common embeddings are what are called standardization and normalization. So for various kind of computational reasons and some theoretical reasons as well, model training, the process of sort of building a good predictive model, it tends to work better if the data are all kind of on similar order of magnitude, similar scales. So what you don't want is to have some data that are order 1 and some other data that are order, 1 billion or something like that. That can lead to sort of bad numerical results. So standardization and normalization are two ways to rescale data so that they're all kind of on the order of 1, basically. So in standardization, what we basically do is we shift the data and we rescale the data so that it has 0 mean, 0 average, and a standard deviation of 1. So to do that, basically we take the raw data, the input data U, subtract off the average or the mean, and then divide by the standard deviation, where the mean and the standard deviation kind of follow the usual definitions here. So to calculate the mean, we just add up all the values and divide by the total number n of values. And standard deviation, we take the squared deviation from the mean, and then take the average of that and take the square root. Okay, so after applying this transformation of standardization, we basically get that the data, so the x's that come out of this transformation, the data have 0 mean, and their standard deviation is equal to 1. So what this roughly says is your data are basically centered at 0, and most of the time they're within kind of plus or minus 2, something like that range. Another way to kind of get the data to be roughly order 1 is to do what's called normalization. And so here, rather than sort of centering the data at the origin and calibrating its standard deviation, what we do is basically subtract off the minimum value and then divide by like the range of the data, the difference between the maximum and the minimum. Where here U min, it's just the smallest value of all the raw data that we have, and U max is just the largest value. And then after applying this transformation, we get that each of the left-hand sides here, the features x, are all between 0 and 1. And depending on the structure of the data that you're working with, it might be better to use standardization or normalization. And you could always just try both and then run your whole model fitting process and see which leads to better overall performance and in the validation set. And then pick it, basically pick the better one. Okay, so let's talk a little bit about models, or sometimes called predictors or predictive models. So a model is just a function f, and here we use a subscript theta, but it basically maps elements of the feature space. So here nx is the number of predicted features into the space of basically targets that you're trying to predict. And again, in general, this could have an ny up here. So you could be predicting vector valued things. But just for simplicity, for this lecture, we're going to assume that we're always predicting scalars. So the function f theta, the model, would produce scalar outputs. And then why we put a theta here, a subscript theta. So this is not meant to indicate a derivative or something like that. In a math class, if you had f of x, f sub x, or f sub y, it might indicate a partial derivative. That's not what this notation is meant to illustrate. Rather, it's emphasizing the fact that this function that we call a model has internal to it a bunch of numbers that we call parameters. And those are the elements of this vector theta. So if your model had the form, f of x is x plus x squared plus, or ax squared plus bx cubed and so on, then the numbers a and b and stuff that show up in here would be the elements of the parameter vector theta. And a good model, again, coming back to our overall goal, would be such that if we stick in our features, x, for some new unseen data, x and y, we take the input data and plug it into the function, we should get back something, the output of the function that is close to what we're trying to predict, the y. And we don't just want that to happen in the training data, we also want that to happen in the unseen data that will come in the future. Okay, so that's kind of a generic expression of what this function f sub theta is. There are many different forms that a model or a predictive model can take. Today, we will talk almost exclusively about linear models, but there are also neural networks. This is the technology that underlies, for example, ChatGPT and other generative AI models. And there are others. There's what's called nearest neighbors predictors. So if you have a large data set, you might say, predict the output corresponding to some input by looking at what example you had in the past data that was most similar to the input data that you just received. So find the most similar example and then just guess that the output, the prediction corresponding to your current data point, would be the same or close to that closest example from your training data. So they're a very simple family of predictors, but they can be quite useful in practice. Okay, so let's talk a little more concretely about a linear model. So here, because we're predicting a scalar valued thing, the output of our model should just be one number. And we can represent it quite simply as just the inner product of the parameter vector theta times our feature vector x. So this is just theta 1 times x1 plus theta 2 times x2 and so on. And then usually when we use linear models, not always, but most of the time, we want to put sort of a constant term into the model that roughly captures kind of the scale of the data or the mean of the data. And so we'd use a feature, a very simple kind of dumb feature that's just equal to 1, a constant feature. And then we would have theta1 times x1 would just give back theta1. So the model would have this particular form. Okay, and then we have a bunch of examples, a bunch of xi, yi pairs in our training data set that we want to use to basically come up with the numbers that we should use for these theta parameters. And we want to choose these parameters theta such that the output of the model in the training data set, the prediction here, is close to the true target that we're trying to hit. Okay. So then we can write this in vector form, basically just take this model and apply it to each example that we have in the data set. So theta transpose times the first feature vector, x1 from the first example, we want that to be similar to y1, the target in the first example. And so on down until yn, this is the sort of size of our data set. We want theta transpose x nth example to be roughly the same as yn. So we can do a little bit of algebra here to write this in a more compact way. So this theta transpose x1 is just a scalar. It's an inner product between two n vectors. So you can transpose a scalar and it remains the same number, the same thing. So here all we've done is applied the transpose to this inner product. Okay. And then we can factor out the theta. So you can kind of convince yourself that this is true. Here we're taking, this would be whatever the dimension of our feature vector is, nx here. That would be the number of columns, and we'd have n rows. So this would be an n by nx matrix. And then theta is an nx by 1 vector. So this whole thing kind of parses. n by nx times nx by 1 would give you an n by 1 vector, which is what we have on the right-hand side here. And then each element of that vector we get by taking this row and multiplying it by the column vector theta. Okay, so then we can write it as this whole thing here we can call x, which is called the feature matrix. So we can write this as x times theta approximately equal to y. And here I'm using capital Y to represent the vector of all the targets that we're trying to hit. Okay. So here we have the vector x would be, again, n rows, nx columns, number of features columns, and y would be n by 1. And sorry, I need to grab a cough drop, 1 sec. Okay, so this should maybe actually be highlighted as well, because this is an important formula. All right. Another important component that goes into the training of a model is what's called the loss function. So this is a function Li, which would, I guess we can view it as a function of the underlying parameter vector theta. And it returns basically a scalar that quantifies how badly our prediction, f theta of xi, misses the target yi that we are trying to hit. And we've talked about norms in several different contexts in this class. We've talked about the Chebyshev norm, the 2 norm, the 1 norm. There are many other kinds of norms. The norms are basically ways of measuring distances. And that notion of distance is different depending on kind of the dimension of the space that you're working in and the notion of distance that we use. A loss function, choice of a loss function is kind of similar to the choice of a norm. So one option here is the squared loss, and this is very commonly used. And so here we have a quadratic penalty basically on missing. So if we overpredict here, this is our prediction, and this point here is the target. So if we are exactly at the target, so if our prediction f theta of xi is equal to yi, we will get 0 penalty. That would be a perfect prediction, so no penalty for missing. And then as we overpredict or underpredict, we go kind of up quadratically. So if we're right in the neighborhood of the prediction, the penalty is very small. But the further and further away we get, the more this grows. And then another choice of a loss function is called the absolute loss. And here, rather than kind of this quadratic penalty, we would just use an absolute value penalty. So this thing actually grows more steeply than the square loss for sort of small losses, right? But when you're out here for larger losses, this thing grows kind of like y equals x, a linear growth, whereas this one is growing quadratically. So let's see. So if you had in your data set a few outliers, so you're making really good predictions most of the time, but just make abysmally terribly predictions once in a while. The square loss function would end up being very large, meaning your overall sort of loss for that prediction structure would be quite high with the blue curve. But with the yellow curve or the orange curve here, it wouldn't be quite so high, because if we're way out here, this line y equals x is going to be way below the line y equals x squared for the curve. Does that make sense? Okay. Okay, so once we have specified a loss function, we can form what's called the mean loss. It's just what it sounds like. You take the loss I for each example I in your data set, and you just take the average. So you add it all up over all of the examples that you have for training, and you divide it by the total number of examples. That gives you the arithmetic mean of the data set, and we call that L, the mean loss of theta. And this will be different have a different number for different values of the parameter vector theta. And depending on what we chose for the loss function, we get different sort of interpretations of the mean loss. So if we choose the square loss function, then L, the mean loss, is just interpreted as the mean square error. So here, the error is the difference between our prediction and the target. We square it, and then we take the average of all those squares. So this thing is the MSE, the mean squared error. And then if we choose the absolute loss, then the mean loss is just the mean absolute error. So this is our error again, take the absolute value and average it over the data set. And by the way, there are other loss functions you can choose. They don't necessarily have to be symmetric. So sometimes you might say, well, over predicting something is not too bad, but under predicting would be catastrophic. And so you might have a steeper penalty kind of down here than you have out here. Okay. So we are getting close to being able to talk about how we choose and how specifically we use optimization to choose the numbers that go into this parameter vector theta. And roughly what we want to do is minimize the mean loss. So once we have chosen our loss function, we form the mean loss, and then we want to form an optimization problem that says, dear computer, please make the mean loss as small as possible in the training data set. There's one more wrinkle, and it has to do with what's called regularization. And regularization is a way basically to improve predictive performance on unseen data. And we'll talk about, and I'll show some examples of how this can actually improve performance. It's not immediately obvious, but basically a model tends to be, or is called insensitive if whenever you have two data points, call it x and x tilde, that are relatively close together, that your predictions that correspond to x and x tilde are also pretty close together. So it turns out, for various reasons, that models that have lower sensitivity, that are more insensitive, tend to generalize better, which again means they do better, not just on the training data set, but also on unseen data that arrives in the future. And this is kind of an empirical fact that people have observed by doing machine learning for a long time. There is also some theory that you can kind of put to this point, but we won't go into that. So a regularizer, call it a function R, maps from your parameter space into just scalars. And it is a function that quantifies the sensitivity of your predictive model. And so when we're talking about a linear model, how sensitive a function is, you can roughly quantify by looking at its derivative. So if a function has a really high derivative with respect to some input variable, that means its slope is like super high. Which means if you adjust that variable just a little bit, you can get really big changes in the output of your function. Okay. So if we just take our linear model here and look at the derivative of this whole function with respect to one parameter, call it xj. Simple partial derivative here, we want partial with respect to xj of this whole thing. I'm just writing out theta transpose x element wise. So this term has no xj in it, it's just constants. So its derivative is 0. Same thing over here, and for every other term in the summation here, except for the xj term. And this thing here is just xj times some number, take its derivative, and you just get back that number. So this tells us that as the derivative is sort of a representation of sensitivity, gives us the intuition that our function, our predictive model, f theta, should be less sensitive if, in general, our parameter vector is smaller, is closer to the origin. So if each component of it is small. So the choice of the regularization function that we use in a machine learning problem is another design choice, just like the choice of the model structure or the choice of the loss function. And there are two common choices. And again, one of them is quadratic and one of them has absolute values in it. So ridge regularization, I don't know why it's called that, also called L2 regularization. Basically, we take the 2 norm of the parameter vector squared, which ends up just being the sum of squares of all the parameters. So this thing basically says, again, push the parameter vector closer to the origin, make all the elements of the parameter vector smaller in magnitude. And then lasso, again, I don't know exactly why it's called that, or L1 regularization basically is the 1 norm of the parameter vector. So rather than squaring all the elements, we just take the absolute value of all the elements. And again, it's a way to sort of nudge the whole vector closer to the origin. And then I talked about in linear models how we often have a constant feature. And that's there basically to allow the model kind of to represent the scale or the mean of the data. And so sometimes when we regularize, and what that means basically is when we're optimizing for the values of the parameters that will go into our predictive model, we add a little term that is related to a function R, a regularizer. And it's sometimes valuable to not regularize that first sort of offset term in a linear model. Talk a little bit more about that later. An important idea of regularization, kind of why would we choose L2 or ridge regularization versus L1 or lasso regularization? One answer to that is that lasso regularization promotes sparsity. So a vector is sparse if it has mostly 0 components. So if theta j is equal to 0 in the linear model here, say theta 1, or I don't know, call it theta n is equal to 0, then this last feature here that goes into the model, every time it enters into the model, it gets multiplied by 0, meaning it has absolutely no influence on the overall prediction. So that means that that feature is somehow not important to the model, and so you might as well just not use it at all. You might as well just knock it out. Yes, question?
Can that also be applied to features that are very, very, very close to 0 and not exactly 0?
Could that also be applied to features that are very close to 0? So if the parameter, rather than being actual 0, is 10 to the minus 8, so 0.0000 or whatever, 1. Yeah, then that same idea. Then the model is very insensitive to that feature. And so that again tells you that that feature is not very influential on the model overall. Now, if your data are on different scales, so suppose that x1 is order 1, but xn is order 1 billion, then if this parameter here, theta 1 is order 1, actually, if this thing is order 1 billionth, so 10 to the minus 9, then actually the contribution of this term is comparable, about the same scale as the contribution of this term. Does that make sense? And that's one reason why we often rescale the raw data, the U data that goes into our model, so that we can make interpretations like this by looking at the size of the parameters to get an idea of how influential the corresponding feature might be. Okay, so this plot looks almost exactly the same as the one that I showed a couple of slides ago about the loss function. But here we are showing L2 or ridge regularization of a parameter theta j versus lasso regularization. And so again, we get this fact that basically, if you're trying to make a number theta j small, here you have like a huge incentive to reduce theta j an incremental amount when theta j is large. But as theta j gets smaller and smaller, kind of the incremental value of decreasing theta j gets smaller and smaller. You get sort of diminishing returns, if that makes sense. And when you get down here, you almost don't care at all. There's almost no benefit left to making theta j small. So if you use ridge regularization, we often end up with a bunch of values that are kind of small but not zero, if that makes sense. Whereas with lasso regularization, the incentive, if you like, to reduce theta j stays the same. So if you do a unit change in theta j, you get the same change in the overall regularizer, all the way down to zero. So the incentive to reduce basically stays strong until you hit the origin. And this is basically why lasso promotes sparsity in that theta vector, but ridge does not. Okay, so with all of that under our belts, how do we actually choose this parameter vector theta? And so to do this, we want to solve an optimization problem. We're in the optimization unit of this class, so you could probably tell that that was going to come up. And we do it via what's called regularized mean loss minimization. This is sometimes called empirical risk minimization. But basically, we form the mean loss function, and then we want to minimize it with some additional regularization. So there are two kind of competing goals. Remember, our overall ultimate goal is to be able to make good predictions on data that we haven't seen yet. And we're trying to sort of get to that goal, to perform well with that respect to that criterion, by balancing two things with the data that we have available to us. On the one hand, we want to fit the training data well. And by that, we mean make the mean loss small in the training data. But we also want to generalize well. And we have this notion that regularization makes our model less sensitive to parameters, and that actually promotes improved generalization. And so to do that, we want to make this function R small. So then our overall objective that goes into our optimization is to minimize a weighted sum of the mean loss and the regularizer, where we have a weight here, lambda. And in ML speak, we call lambda a hyperparameter, or the regularization hyperparameter specifically. So this is a non-negative number, and it basically tells our optimization, if this is our objective, how much we care about the first term versus the second term. So if lambda is equal to 0, we only care about fitting the training data really well, right? And we're not using sort of any other information to say, oh, but we also want to fit unseen data well. And then if lambda goes to infinity, basically we don't care about fitting the training data at all. And all we want is a small parameter vector. So that would give like a really dumb result. It would just give theta equal to 0, the 0 vector. And then in between those two extremes, basically as we increase lambda, we're saying put more and more weight on the regularization and less weight on the fitting the training data. Okay, I'll show some examples of all these things in just a second. So let's go back to the simple case of a linear model. By the way, all this stuff that we're talking about is used not just with linear models, but with kind of all the random weird model structures, neural networks, support vector machines, regression trees, etc. I know those are just random meaningless words to you guys right now. I'd be happy to talk a little bit more about those model structures, but everything is sort of concrete and simpler in the case of linear models. So we're going to start there. And then if you want to use other model structures in your own work in the future, you at least know kind of the process that you can follow. Okay, so with a linear model, it turns out that the function here that we're trying to minimize, which is the regularized mean loss, actually is a quadratic function of the parameter vector theta. And so we can show that in just a few lines here. So the mean loss, it turns out you can write as, with the square loss function and a linear model and L2 regularization, so ridge regularization, not lasso regularization. This term here is basically the sum of all the mean of all the squared errors. And this term over here is basically our quadratic penalty on theta. So we can do a little bit of math here. Basically FOIL out this term. First outside, insides last, right? If you're multiplying two sums, you do that, and that happens, works just as well with vector valued stuff as it does with scalar valued stuff. So here we can apply the transpose to all of these elements and then multiply all the first stuff together. So that's what gives us this theta x theta term. And then we'd have two terms that basically have a y multiplied by an x theta in it. And those are all scalars. So everything here on the right-hand side is a scalar. So those terms basically we can add together. And then we have from the last term here a y transpose y. And our dividing by n, this is to take the mean of all the sum of squared errors, or sorry, all the squared errors. And so we still have the dividing by n here as well. And then on this last term on the right-hand side, all I've done is insert an identity matrix in between the two thetas. That doesn't change this term at all, right? I times theta is just theta. But we're going to basically factor out thetas from each of the terms here in order to simplify this expression. So when we do that, here we can multiply this term by n and then factor out a 1 over n. And then we have a couple of terms that look like theta transpose times a matrix times theta. And so that shows up here. And we have one over here as well. So that's where we get to n lambda times the identity matrix over here. So this now is a quadratic function of theta. So we have a weight matrix here that's sort of the weight on the squared term. We have another matrix here, or sort of vector here, which is the weight on the sort of linear term. And then we have an affine term, just an offset over here. So this whole function has the form, again, of a quadratic function with the variable being theta. And we've talked a couple of times over the last couple of weeks about quadratic functions, how you can take their derivative or the gradient of the function, and it sort of looks just like it looks in the scalar case. So here, this is kind of like p times theta squared. So its derivative becomes 2p times theta. And then we have q times theta over here. Its derivative or the gradient of that term just becomes q. So this is it turns out, a convex quadratic function, as long as this weight matrix here, P, is what's called positive semi-definite. And actually, because of the particular structure of this weight matrix, you can show that it always is positive semi-definite. So this is a convex quadratic function. That means we can take the derivative and set it equal to 0 and solve, and we get the sort of optimal value of theta here. So there's an analytical expression for this thing. You can compute it very quickly. And we're guaranteed that if the regularization weight lambda here is positive, that the inverse that shows up on the right-hand side always exists. If we are not regularizing at all in this case, however, then the inverse is not guaranteed to exist. It actually depends on the structure of the feature matrix here, X. So only if this thing is full rank, meaning it has linearly independent columns, are we guaranteed that this matrix exists, the inverse. And then, yeah, if you want to omit the first theta parameter from the regularization, again, sometimes you want to leave that one sort of unpenalized or unregularized. Then we just replace this identity matrix that shows up here. We replace it by this product E transpose E. And I'm not going to go through that, but if you find yourself in that situation, you can refer back to these slides. And then if we are not using the square loss, like what if we're using absolute loss? Or what if rather than L2 regularization, we're using L1? Well, then we don't get a tidy formula like this. We don't get an analytical expression for the optimal parameter vector. Instead, we get a convex optimization problem. And we can feed that to CVX or whatever other modeling language we like. It can pass our problem to a solver and give us back an optimal solution. Okay, almost to our example, I promise. So again, our true goal is basically to match unseen data well. So sometime in the future, an unseen pair, an input, a raw input will arrive, and we'll want to predict the raw output. And we want that to be close to the true value here. So to compute that, we take our raw data, we embed it into a feature, we plug that feature into our model, and then we undo the embedding that we are using for our targets in the training data. We undo that with a psi inverse, and that gives us our prediction. So this whole thing on the left-hand side is the prediction, and this thing on the right-hand side is the target. So we want that to be true in unseen data. We can't really test that because we haven't seen the unseen data yet, so we withhold some data, and we call that our validation data. So the idea is that as we're making all these choices, what embeddings should I use? What model structure should I use? What regularization weight should I use? These sorts of things. As we're making those choices, we want to periodically check our validation data and see how well are we doing, and kind of iterate in that sense. Okay, so the workflow using out of sample validation, again, is to split the data into training, which is used to fit kind of the numbers that go into our model, and validation data, which is used to check kind of how well our assumptions and things like that are doing. So that might be somewhere between 70 to 90% for training and the rest for validation. And okay, so our workflow, we choose some starter embeddings, things that we think might work well, standardize this, normalize that, and so on. Pick a model, maybe it's linear, maybe it's a neural net, maybe something else, and pick some hyperparameters. This could be the weight on our regularization. And then, we begin sort of an iterative design loop where we make a little bit of change. Maybe we fiddle with one thing. We refit our model in the training data, and we look at how well it predicts in the validation data. And if the little change that we made was good, it led to an improvement in the result, we keep it and we repeat. If it was bad, if it led to worse performance, maybe we throw it away. We say, well, that was a bad idea. I'll try something else. And then we kind of repeat this design loop until we arrive at something that is satisfactory, basically. It makes good predictions in the validation data. So one way to do this kind of validation thing is just to do one split of the data, training and test, and then stick with that forever, or training and validation. Another way to do it that's slightly more robust to patterns in the data that you might not have expected is what's called k-folds validation. So the idea here is that we divide the data into k chunks, or we call those chunks folds. And then we repeat this process. And this actually would be inside this design loop here. So this would be how we check the performance in the validation data, the third point there. So we train on all of the data except for fold k. So as we're in this loop, we're at 10, okay, 10th fold, we hold that data back. We withhold that data. Then we calculate the mean loss on fold k, the one that we didn't train on, and that becomes our validation loss. We do that a bunch of times, and then we average sort of over all the folds, all the different ways we've held data back from ourselves. Okay, so L bar here would be the mean over all the folds of the mean losses. All right, so with all the bells and whistles of this workflow, overall, basically the workflow for machine learning, for regression specifically, we choose a loss function that rates how badly we're missing the targets that we're trying to predict. We choose some regularization, and we split the data into training and validation. This may be done in a k-folds kind of sense. And then we repeat this design loop. So we choose our embeddings. And this process of choosing good embeddings, by the way, is called feature engineering. Also in this feature engineering process, we may throw away some features that it turns out aren't very useful for making predictions. Then we choose a model structure, and we choose our hyperparameter that we're going to use for our regularized mean loss minimization. That's called model selection and hyperparameter tuning. And then we do our training. So we solve our optimization problem in order to come up with a number for our parameter vector. And then we repeat this whole design process until our performance in the validation data set is acceptable. And often, actually not always, but often at the end of the day, after we've done all of this, we would then go back to the full data set, use all the data that we have available to us. And now we have good settings. We've got good settings for the model structure, for the hyperparameter weights, and so on. And then we retrain again with all the data available. And then you go to production with that sort of final model. All right, so that was all very abstract. Let's talk about this a little bit more concretely in two example problems. So the first problem here is called polynomial fitting. So we basically are told that there's some function that maps numbers on this interval -1 to 1 into real numbers. So here the interval -1 to 1, and then these are a bunch of observations of the function, but they're noisy observations. So maybe these are measurements that we're taking with a sensor that's not particularly accurate. The inputs that we're given, U1 through U50, this is just 50 data points along the U axis. And then we have the corresponding values. These are just the dots here on the V axis. And we want to basically come up with a model that accurately predicts data that's in between these data points. Okay, so here, just for illustration, we'll use a linear model and we'll choose the square loss function. And we'll use basically come up with polynomial embeddings. So we'll just say, look, we don't know what the function is, but let's assume that it has a polynomial structure, and we'll allow that polynomial to have super high degree. So it can have a whole bunch of different terms, x to the 27th or whatever it might be. And we'll standardize the targets for the embedding. The features are all kind of already between -1 and 1, so we won't do any embedding on those. I'll use k-folds validation with 10 possible folds. And then we'll do 2 stages of kind of the regularized mean loss minimization. One where we use the lasso, the L1 regularization, which basically is going to zero out a bunch of the weights on a bunch of features, tell us which features we can ignore. And then once we have kind of a good set of features, we'll use ridge regularization to do the final kind of model polishing or training. Okay, so we start out here with basically all the possible features up to a 25th degree polynomial. So this is like x squared, x cubed, and so on, all the way up to x to the 25 or u to the 25. And then the scale of these things can be quite different from one feature to the next. So we're going to normalize all of these. So basically rescale them all so that they're all between 0 and 1. And we do that by subtracting the minimum and then dividing basically by the range of the data. And then we'll use standardization on the targets. So basically make them zero mean and have kind of a unit standard deviation. So here I'm illustrating the problem of overfitting. So if we just take that, super high degree polynomial and say we're trying to fit 26 different parameters corresponding to all the different features in that polynomial function, we can fit all the training data really, really well. So the training data are blue and the validation data, I guess, are orange. So we're getting close to basically almost all of those examples, but you can see that we're wildly missing some of the validation data points. And this function is just like really noisy. It's very sensitive, right, to small changes in any of these features. So here we have a really low loss, a 0.2 loss in the training data, but in the validation data, we're at like 5,000. So just radically worse fit in the validation data. So we have overfit the training data here. So now we're going to put in a little bit of regularization and hope that that overfitting problem goes away, or at least gets better. So here we're starting with a low weight, and this is our L1 regularization, which again promotes sparsity. It's going to knock out or zero out some of the parameter values. And then raising the value here a little bit, and I just am sweeping kind of logarithmically spaced values of this regularization parameter. So you can see that the predictions are getting sort of less crazy, less wiggly as we go. The function is looking smoother and smoother as we go. And this is looking pretty good. And then as the regularization weight gets higher and higher, eventually it's like too smooth, right? It just becomes kind of a constant here. So this is not predicting particularly well. Basically, we're just predicting the mean of the data. Okay, so here's a plot of basically that sweep of the parameter lambda. So in the first plot, the x-axis here is the regularization weight. So very low weight means mainly we care about fitting the training data well. And very high weight means mainly we care about the parameter being small. And in between, we're kind of balancing a trade-off between those two. So, and then this is the mean over the different k folds of the data, the different ways to sort of slice the data. This is the average over those slices, the number of non-zero theta. So we begin with basically almost all of the theta is non-zero, and we end with basically everything or all but one equal to zero. And in between, we're sort of knocking out thetas as we go here. And then here I'm plotting the mean loss in the training data and in the validation data. So training is blue, it's low for a while. Validation begins very high with a sort of overfit model. And then even just as we add a little bit of regularization, we knock down the validation error. So we're getting better and better in the fit there. And then it's a little hard to see, but we begin to increase a bit here. So there's sort of a minimum, and then we begin to go back up. And then this is showing the mean magnitude of each of the parameters theta j, and averaged over all the folds, the ways to slice the data. So you can see some of these parameters are showing up as being influential. A lot of them are getting knocked out to zero. This 23rd degree term over here actually is non-zero. Okay, so basically what I did in the code here is I said, okay, anything where on average over all the different ways to slice the data, we got something very small, we'll basically throw away all those features, declare them not valuable features. So we'll knock out the 8th order, the 9th order, the 10th order terms. But we'll keep the ones that look like they're pretty significant. And then with that restricted set of features, then we'll do a fit again using L2 or ridge regularization. So this is again showing the same plots. We're going to increase this weight between the fit and the L2 regularization. So getting smoother and smoother, and again, too smooth at some point. So similar plot, except here we're showing the average magnitudes of the parameters. And so you can see that all the parameters are getting kind of sucked down close to zero here. And the more regularization that we do, the higher this weight is, the closer they all get basically to one. And then again, I'm showing the loss over all the different folds in the data. And so you can see that it's pretty small, and then at some point it starts going back up. And this lambda star here is actually the lowest value of this function. And then these are kind of the results, the magnitudes of the parameters that are remaining. And so you can see we basically ignored all of these features, and also the cubic feature for whatever reason we ignored too. So the end of that whole process, now we have our prediction, our model that we've finalized. And this is the true function, which I didn't show to the code at any point during the learning process. But I knew because this is a made up sort of problem. So here's all the data. These are the noisy observations of the blue function here. And then the orange function here was our fit, basically at the end of this process. So it's not perfect, we're not exactly on top of the blue, but it's kind of, it's got the right-ish behavior. By the way, it's interpolating well within this range of -1 to 1. But if we looked outside of that range, say we went up to +2 or -2, the blue and the orange might diverge. Actually, I didn't draw that plot. But basically within the area where we have good data, we're able to represent the function behavior well. Extrapolating beyond that range, don't know, right? It might be risky. And these are the final parameter values that we fit. All right, so that is an example to illustrate kind of the workflow. Oh, sorry, yes, Grant, question.
Couple questions. So whenever you point out lambda star on both ridge and the other version, did you select those lambdas when you move forward, or is that something that you just keep in mind?
Yes, that's a point I should have made. So the question is, I have these lambda star values plotted on this plot and on the other plot for the L1 regularization. So the question is, did I use this in some way? And the answer is yes. So basically I did some kind of trial fits, sweeping the value of that parameter. And then I said, okay, find the best value of that parameter. And then I basically kept the weights associated with that value, the parameter value associated with this lambda star, and threw away all the other ones.
Is there a case scenario, say, with the other version? Sorry, it's starting to be blank right now. But,
yeah, it's okay.
Where you would use the one where you get the biggest bang for your buck drop, like whenever we saw, whenever we saw that big tank in the mean loss, but you're still, I guess, you're able to use a small weighting. I don't know what that tells us about our two parameters that we're trying to balance, but then it was just always a huge amount.
Yeah, so just to paraphrase a little bit. So early on, as we added just a little bit of regularization, we saw this really big drop in the overfitting problem, the validation error. Um, and so would there be a scenario where we might want to just stop here, or maybe like one level up from there, something like that? Um, yeah, I think that's perfectly reasonable. So here, what I'm calling lambda star, like the optimal lambda, I chose by finding the lowest value in the validation set. But that's not necessarily the only way to do it. You know, you might want to balance training accuracy and with validation accuracy. You might also say, look, I don't want to get rid of too many parameters. I know that you have some prior information that you have some intuition that a bunch of these features are going to be useful, and you don't want to ignore, all but 5 of them or something like that. So in that case, you might say, my engineering intuition nudges me to basically choosing a lower value of this lambda somewhere over here. Yeah.
Just how do you evaluate like data values that you use when constructing the model? I know you show like our model's outputs, but whenever you can comparing the true function to the model function on slide 26, yeah. Do you have what they actually are? Like theta j's that you use to
Oh, do I have the final numerical values of the theta j's of the end
like
model?
to compare between true models?
Oh, I see what you're saying. Yeah. So these are the fit values of the theta j's. The true function that I fed in, I don't have those numerical values on me, but it was the seventh degree polynomial. So it got the degree right. I think that's right. All these are 0 beyond. And I think also I had zeroed out the cubic term intentionally, and I sort of picked that up as well. But other than that, I think like the numerical values of the thetas are not that close to the true values of the thetas. But the outputs of the function are reasonably close, right? Yeah, within the -1 to 1 range, not necessarily beyond that range. Yeah. So I think I will go through the next example next time. I just want to, this is like a little bit of a leap, but I just want to tie this a little bit back into what we talked about actually after the exam with generative AI and how tools like ChatGPT tend to be good at like easy problems where there's a lot of information out there on the internet about those problems, and the information that's out there is pretty trustworthy. So in some sense, that's like being sort of in the core of this data. There's like a lot of these points, a lot of these examples in that range that a tool like ChatGPT can be trained on. But like if you're doing weirder problems where there are just fewer examples out there on Wikipedia pages or academic websites or whatever it might be, then you're further away from like the core of the data that you're training on. So it becomes a little bit, rather than an interpolation problem, and this is all very loose, but rather than sort of, reprocessing, resampling, reshuffling data that there's a lot of stuff kind of in the neighborhood of what you were looking for. Now you're kind of out here in the world of extrapolation. And it's not clear. I mean, maybe the next generation of these tools actually will be able to do that really reliably. But what we tend to see, at least in this class, in the exam that we took, was that for the harder and weirder problems where there's just not that many examples on the internet of solutions that are reliable, trustworthy, et cetera, that the performance of these models kind of degrades. It's a little bit like trying to make predictions outside of the range where your data are available. That makes sense. Okay. All right, so just to summarize this example, and again, on Thursday, we'll start with the final example, which is a DER example specifically. Basically, so what we call linear models are functions that are linear in the parameter vector, and they're linear in the feature vector here, x, but they can be highly nonlinear in what we call U, the raw kind of input predictive data. And that's because we take U and we can process it through a bunch of embeddings, a bunch of weird nonlinear functions. We took U to the 25 and made that one of the features X, for example. Okay, so what we call linear models actually can have all sorts of cool, weird curvature and stuff. We also outlined in this example a general approach that tends to work pretty well for a lot of regression problems. So we embed the raw inputs into a large number of candidate features, some of which might be kind of silly. Like you just know, well, this probably isn't going to add much predictive information. The weather in Brazil probably isn't very relevant to a community's load forecast, here in Indiana. But what the heck? I'll just come up with a huge number of these possible features just to see. And then use lasso regularization basically to fit your model using cross-validation, and basically just let the optimization, which is trying to promote sparsity, knock out a bunch of features that end up not being useful. So it says, yeah, humidity in Sao Paulo doesn't matter. You can ignore that one. But the temperature in Lafayette, that one isn't influential. We're going to keep it. So we do that in kind of a feature selection step. And then the features that we're left with, we do kind of a polishing step where we use ridge regularization to basically come up with a nice sort of predictive model, a nice smooth model using the features that are left over. So step 3 here can be done very fast. So we talked about how with the square loss function and L2 regularization, you have an analytical formula that you can run super quickly in MATLAB or Python or whatever. So functionally on a laptop, it's basically instantaneous, even with a pretty big data set, thousands of examples. Step 2, because it has this sort of lasso regularization term in there, it's not a quadratic optimization problem that we have an exact solution for, but it is a convex optimization problem that we can feed to numerical optimization and get back a solution pretty quickly. So not as quickly as step 3, but not too long. And this approach also works for models that are not linear. So it can work for a neural network type model or a support vector machine or other things. But both step 3 and step 2 in that case tend to take much longer. You guys you have a gradient descent problem on your homework that is due on Thursday. And that roughly is the technology that's used just at vast scales to fit neural network models that underlie stuff like ChatGPT. So it's not exactly gradient descent, it's something called stochastic gradient descent. So you kind of are sampling random things that are close to the gradient and using that. It may run many versions of it from many different possible initial guesses so that you land in sort of different local minima and things like that. So it's doing lots of clever kind of algorithmic stuff under the hood. But in broad strokes, the basic idea is pretty similar to what you guys are doing at homework this week. Okay, so that's all for today. We will start with this example, a much cleaner and simpler example on Thursday. And then we will go on to talking about optimization under uncertainty. So if your models aren't perfect and your predictions aren't perfect, how do you basically make predictions or good decisions in that setting? Okay, so thanks all. See you on Thursday.